Thank you for that great introduction. I'm also very happy to be here because my work, although I'm in the Department of Civil and Environmental Engineering, I'm really in the School of Engineering, but as you will see, my work is design work, which doesn't always get recognized in the School of Engineering, and I think it also relates to architecture and design and the visual arts. And I know that here you are kind of in all these fields, so it's very exciting for me to present my work to a multidisciplinary audience. Let me see how that's going to work. Okay, so as Bob mentioned, in 2009, I moved with my family to New Jersey to work at Princeton University. And besides working, sometimes we go to the shore. It's on the East Coast, it's about an hour away from Princeton at the New Jersey shore. And this is a picture taken in the car as we're going to the shore. And what really struck me are these bridges. They are, what I wrote, they're very big. They're very, the big beams. And that kind of already in 2009 surprised me because the construction industry is one of the most resource-intensive industries. And I kind of know that, if you design this differently, this bridge, this sketch of mine, could actually look like this, right? You don't actually need all that material if you think of it as a beam. It's fixed on the sides and the interior support. You can actually, really reduce the amount of material that you are using. And if you reduce material, then your bridge costs less. And then also you are having a smaller impact on the environment. Now, when we get to the shore, this is what it looks like. This is Rockaway Peninsula. So what do we see? Well, first of all, we see a lot of people. We also see a lot of buildings right next to the shore. And it's actually predicted by 2050 that the world population will increase by 2.1 billion people. All these people are going to need houses and places to work. So we are going to need a lot of more floor space to accommodate all these people. And that is then, of course, against the backdrop that the construction industry is, in general, this is a graph of the McKinsey report. You see there are all kinds of different economies, but you see the total economy is going up, right? On the x-axis we have time, on the y-axis we have labor productivity. Well, there's one really going down. That's the United States, unfortunately, and that's construction. All right, so construction productivity is really, really going down. And I put there a picture of a construction site anno 2021. I have pictures of construction site 1950. They're different, but not so different. So the construction practices that we have not really changed that much from how they were 50 years ago or 70 years ago. And so that's one challenge. Another challenge is that the construction industry uses about 40% of the global non-renewable resource consumption. So, it is estimated that in 30 years, sand, which is something that we put in concrete, will not be affordable anymore. I guess we're using all the sand that is out there. More challenges are, we are creating a lot of construction waste. It is estimated that in the US that about 29% of the landfill is filled with construction waste. So very, very wasteful, the way that we are constructing. And finally, we're also producing a lot of CO2, because we are making, especially concrete, if you make concrete, we produce a lot of CO2 emissions. And this is a picture from Shanghai in 2017. They had to close the construction sites for a couple of months because there was just too much pollution. So that's there. And so we're not only contributing, but also in the built environment, we are suffering the challenges of climate change. And this is not a picture from a movie. This is a picture from the East Coast, actually very close to the beaches that we go to on the Jersey Shore. In 2012, there was a hurricane there, and do you remember the buildings that I showed you on Rockaway Peninsula? There's no real barrier between the two. So when this hurricane came, it destroyed a lot. It destroyed a lot of houses. There were a lot of social losses, and of course, huge economic loss. And these hurricanes, they are going to be more intense and they're going to be more frequent. So these are all huge challenges that we face in the built environment. And so after Hurricane Sandy, of course, all the coastal communities were very eager to get business back as usual. So some approaches were just like, we just build what we had before. We rebuilt the boardwalk, right? Not really taking into account that this will happen again quite quickly. Or some other communities, like this one here, this is in Brick in New Jersey. Their idea was, okay, let's build a big wall, right? And in this case, they actually built a wall out of stones, as you can see. But of course, if you build a wall out of stone, that means that you cannot go on the beach anymore. Sea animals cannot really go that way anymore. If you have property there, your view is not that great anymore. So I don't really think that the idea of using a very heavy wall is going to solve a problem, right? But this is one of the solutions that some of the communities were adopting. So I think that we need to couple to change things, right? We need to design. We need to change the way that we design and what we design for. We need to change how we design and how we build. And the way that I'm proposing to do that in my research is that we are going to use slender surfaces. So the idea is that we're going to use very thin things rather than a lot of mass to design better. And we also have to design for bigger extreme loading. When I was a student, we didn't really have to design for hurricanes and stuff like that. But the loading is getting heavier and heavier. And of course, depending on how the climate evolves, wind loading will change, storm surge loading will change. So we're going to have to design our structures to take these kind of loadings. We also can change how we design. So I already mentioned that the idea of using mass, I don't think is such a great approach. I'm going to show you for the project I'm showing you that I'm kind of advocating for using geometry, using shape rather than mass, and geometry and mechanics. Because if we start using geometry, we can do quite amazing things in mechanics of structures. And then finally, we're also going to have to think about how we build. I'm very much at the moment involved in researching how we can use self-assembly processes. So basically processes where the structure constructs itself so that we do not have to build very wasteful and very expensive formwork and scaffolding. Okay, so I'm going to show you some projects. And of course, I'm not the first one to use form. Throughout history, people have used form to build. And on the x-axis, you see time. On the y-axis, you see weight. And notice that on the y-axis is a logarithmic scale, right? So it goes from 0.1 to 1 to 10 to 100 to 1,000. And if you kind of plot buildings that have survived from those times, you can almost plot a line on this logarithmic scale to the building. So the top, we see the pyramids, they're solid, very heavy. If we make our way down, we have the Pantheon, number 2. Then we have 4, the Hagia Sophia. We go down 7. We have the this number here, number 8. Those are the Gothic falls. And then, as we get closer to our century, we are building. So this is now a setting of 21st century. These are some of the buildings that we can design today. And I'm just going to talk about a few of them. So number 11 is the is the bird's nest in China, right? It's actually quite heavy. A lot of the steel that's used in there is not really structural, it's for decorative purposes. And then some of the other structures are some of the structures that I've been involved with. So I will talk about 14. And then you see I've drawn a line at 1 kilonewton per meter square is kind of the weight of a heavy user. As you know, we can either press down or you can suck your structure up. So if you're designing a very, very lightweight structure, such as, for example, a membrane structure, and you have a wind which actually wants to lift it up, if you don't design the structure properly, it will actually lift up, right? So we have come to a stage where actually we can design very, very lightweight structures, but they have to be designed in a proper way. Otherwise, the wind comes up and kind of sucks it up. It will just fly away because it's so lightweight. Okay, so I'm going to talk about this project here, which is a project that I worked on in industry before I joined academia. I was working for May & Partners, and this is the Dutch Maritime Museum in Amsterdam, the Netherlands. It is a 17th century building, masonry building, stone building, and it used to be a gunpowder house, a warehouse. At some point, the Dutch were a very wealthy seafaring nation, and they would pass with their ships here, stock up on gunpowder, and then set off on their travels. After that was not very fashionable anymore, this became a prison. And then after that didn't really serve its purpose anymore, it became a museum. So it's now a museum that kind of celebrates the history of the Dutch, mostly their seafaring history. So there's lots of models of boats, lots of models of maps, because they were really into map making at some time. And the building is really, it's not one building, it's actually 4 buildings. So if we look, this is a plan view, we were just looking, that way, but actually it's 4 buildings with a courtyard in the middle. Actually, a lot of historic buildings are like this. It's not very deep, that's of course, because at that time when it was built, there was no electricity. So they totally relied on daylight to light their buildings. And so that's why these buildings are not very deep, so that the light can go quite deep into the room. So when they were starting a renovation of the museum, the architects suggested that it would, in order to have more space for conferences and cloakroom, for places of cities, it would be great if that courtyard could be just open to the elements. And if you know Central Europe, it could be not like here, it's very rainy, very cloudy. So the architects suggested maybe it would be interesting to cover that room. So then the client made a design competition and invited the 5 officers to make a proposal for how to cover this roof. This is in historic context, so that means that the roof cannot be seen from outside the building. And secondly, the roof should be as transparent as possible, but because they want to have the light still coming into the building. And so in the museum, we found maps like this map here, right? This is a 16th century map that the Dutch made. And you see the way that they thought about the world. That side is really long. But the other thing that you see is that there's a geometric pattern in this map, right? So there's all these points, actually 16 points, and then a central point, and all these points are connected together. Those are wind flows. So basically, the Dutch thought that the winds start at those points and then blow in certain directions. And so they would use this as a GPS and kind of sail along these lines to get to wherever they needed to get to. Okay, so we thought this is a very interesting pattern. It would be interesting if we could use that pattern in the design of the roof. Remember the roof, this courtyard, it's not quite a square, but it's kind of like a square. So can we impose, extract from this map, this grid, the square grid, and develop that into a roof? Now, the courtyard spans about 90 feet. Now, as you know or don't know, you cannot span, so this is now imposing that grid onto the courtyard. But as the courtyard is 90 feet, so you cannot span that with a beam, right? Because then the beam becomes very, very deep, right? And we wanted to have an economic structure. So we were thinking we probably want to make this into a dome, a compression dome. It's a very efficient structure. And actually, we want to make it into not a continuous, not a concrete dome, and no lights coming. We actually want where all these lines are, we want to have very fine steel members, and then we will clad the dome with glass. And so what we did is, and I was very fortunate, I just finished my PhD and developed these algorithms to make from a planar pattern, which we have there at the top. We model this as a system of springs connected to nodes. We applied loads at all these nodes, and we have a hanging chain model. Now, Now you can say, well, we do that in Cameroon, or we do that in Idaho. No big deal. That was about in 2000. Nobody had done this, right? So actually, Cameroon algorithm is based on this, right? So now it's like, yeah, no big deal. We do that, but at that time, that was a big deal. So anyway, so there were some challenges, right? First of all, the roof would not be very tall. It's really from outside, we weren't really allowed to see the new roof. And secondly, also the new shell could not really put a truss on the walls because the walls would collapse, right? So we have to do some manipulation there. The other manipulation we had to do is when this is a hanging chain model and some of the facets are, this is not triangulated, right? Like some of them are triangles, some of them are quadrilateral with 4 and some are with 5. And as you know, a plane cannot be defined through 4 points, it can be defined through 3 points, that's flat. But if you have 4 or 5 points, it's possible that your facet is not planar. We were going to clad this with flat glass panels. So we had to also incorporate an algorithm to adjust the form slightly so that all the facets are planar and we can clad it with planar glass. Okay, fast forward a couple of years. We won the competition, we built the thing. And this is a view from the outside, obviously a bird's view. Again, you can see it's a very shallow though, because you were not allowed, if you stand in front of the museum, you cannot see it. This is a view from the inside when you're lying on your back, right? So you can see the map. And what is very nice is for this museum, you can actually go into the courtyard for free. And a lot of people that work around this museum will go there to eat their lunch. And that is actually, for me as an engineer, one of the really rewarding, this thing won some architectural prizes, but a really rewarding thing, I think, when people really use that space, when they come out there, sit there to eat their sandwiches, right? Then I think you've really created a space that contributes to the well-being of people. And the other thing that we did, I'm going to show you in a second, is that at the intersection of all these nodes, we inserted LEDs. So at night, you can light it, and then it looks like this, right? And so, of course, this, we hope, is a reminiscence, you maybe dreaming of the boat, of being on the ship and seeing the starry sky, right? Okay, so when we built this, I thought, wow, this is really an interesting structure. It's an indeterminate structure. That means that if one of the members breaks, then the forces will flow around and still comes back, and this thing doesn't collapse. One member or a few members break. Right? Secondly, the members are very thin. It's because it's a shell, so we don't actually have to use a lot of steel in the structure. That's also one of the reasons why I won the competition, because the total price is quite low. And then also it is actually very stiff due to its form. So these kind of structures, I was like, wow, they seem to have a lot of potential to maybe address some of the challenges that we're facing. And besides the fact that the challenges of today at the civil and architectural scale, our challenges are different than mechanical and electrical engineers, because we work at the enormous scale, right? We work at the 10 to 100 to 1 kilometer scale. And that means that they already said that you can't just scale up things. You can scale things for compression and tension structures, but not for bending. So for example, you see there a small bone of an animal. If we scale that up, because area and volume are area to the power 2 and volume to the power 3, they don't really scale up, right? The other thing is we work on the very long temporal scale, right? We don't design iPhones that maybe we raise every 8 years. But like we design things that hopefully last 50 years, maybe 200 years, maybe 1,500 years, right? So that also means that the materials that we are using have to be, the materials that we use have to be durable. They have to last for a very long time, and they also, of course, have to be sustainable. So those are challenges that other engineering disciplines don't really have. And so I'm going to show you how in my research group, the form finding lab, we work with slender structural surfaces. So okay, I'm holding this very closely. That means that we are working with structures that have one dimension much smaller than other dimensions. And because of their geometry, they have properties that other structures don't have. And so the things that I'm going to show you what these structures can do is not because of the materials that they are made out of, it's because of their form, or it's because of the way that elements are arranged in that structure. So I'm going to talk about how we can make things move and amplify motion. I'm going to talk about how we can do things that actually adjust their stiffness. And I'm also going to talk about how we can use form so that we can have large or low carrying capacity, and also how we can actually construct shells that assemble themselves, which is kind of weird, right? So I'm first going to talk about flexible shells. And actually, when I'm coming here, I was thinking, oh yeah, this is really perfect. So the idea is, how can we design buildings that keep us comfortable? Of course, the weather conditions change all the time outside, right? And one idea is to make a box and just control the environment inside the box. But another way is to actually use a facade as a filter to kind of control the effect of the external environment on the buildings. And so we were looking at, can we use what's called adaptive facades, so facades that adapt themselves to the external environment as a function of the external weather conditions. And we started looking at, this is a rendering for an imaginary museum in Marfa, Texas, where maybe you want a facade like this, where you have some rooms behind there that need a lot of light, and maybe you have some projection rooms there at the top where you want your facade to be closed, or maybe you want at twilight, you want actually more light to come in, so you want your facade to be really open, or maybe at noon you actually want your facade to be closed. It has been shown that adaptive facades, if you use this, you can save about 40% of your building operation. Now, adaptive facades exist, for example, the Institut du Monde Arabe, but they usually exist of rigid mechanical parts with hinges. And if you've been to the Institut du Monde Arabe, you know that always there are some bits that are broken. That's because the mechanical parts break. And so we were looking at how can we make shells that don't break. So we started looking at plants. Now you might think, well, plants don't move, especially the factory, they don't seem to move, but a sunflower moves, right? And so together with the biologists, we look at plants to identify whether there are strategies in which they move, and they move to catch the sun, they move to get food, they move to pollinate. And so we found there are really 5 strategies. One is what we call differential expansion, where you have one set of cells that kind of swells and therefore the skin bends. Or you can have very slender elements that bubble. The second one is the bird paradise flower, which kind of pollinates with the bird going to sit on the very slender element and then it twists. Or we can have layered material anisotropy. So basically, this is how orienting fibers in different directions. This is what happens to the pine cones that open with one starts swelling, some of the fibers swell and they kind of pull against each other. The fourth one is the bean slider, and I'll come back to that. And then the fifth one is where you have like a release of energy. That's mostly for pollination. We were interested in shell geometry. So you all know bean slider, right? It kind of is open, and then there are triggers on the bean slider when the plant senses that there is fly there. It sends a signal, and it actually makes one side larger, and because of the geometry, it kind of bubbles into the other shape. So we were interested in this because, of course, we don't want movement that's so fast, right? We want to have control movement. So we disqualified the bean slider as a mechanism, or at least the geometry of the bean slider. But we found another plant which also uses geometry, which is this one here. It's the Cylindrium graminifolium. It's a flower that grows in Australia. You can see it there on the left-hand side. It uses this mechanism for pollination. You see the light blue part, that is a passive part, so that doesn't change shape, but the active part, the pink part, that changes shape. And that geometry is very much like this geometry here. This is actually a middle of a Coke bottle. If you cut out the middle of the Coke bottle, it has this antiplastic curvature. If you press on it, it will actually open very widely. So with very little movement in one direction, you can get very large movement in the other direction. And that was very interesting for us because we want to be able to, with very little energy, or very little displacement, open this thing. So we use that as an active part, as an actuator. You see there it's in the blue, and then we attach to it a passive part. Right? So the red, the tongue thing, that doesn't really move. Only the blue thing can move. by, and we put two kind of actuators there, we use smart memory always. By shortening either both of them, this thing will bend and lift the flap up, or by shortening only one of them, it will twist. And that is exactly what we wanted for adaptive facades. We want to have louvers that can either open or that can twist. And let me see. So, yeah, there we are. So, okay, looking at plants is one way of doing that, but we're going to be a little bit more scientific. We actually found that Lord Rayleigh had said that when a shell is thin enough and it's vibrating one of its great repulsible modes, the middle surface behaves as if it were inextensible. That means that the surface will actually not become longer or shorter. It will not have any kind of membrane action. But when it will deform through bending or twisting, and that's exactly what we want for the adaptive facade. So we did some studies, for example, if you want to get these kind of movements, okay, then you have to use a cylindrical strip, or if you want to get the second row, these kind of movements, you have to have the interior of a quarter of a torus. But the geometry that we were interested in was this one here, right? So we did lots of parametric studies to establish for our purpose, what is the best combination of the two radii of curvature to get this opening, this bending as well as this twisting action. And so here you see, this is again a rendering of supposedly an office in New York, where you have these adaptive facade elements on the outside. Here they are twisted open. This is when they're fully open. This is when they're half open, and this is when it's at night. Okay, so that was how we can use flexible shells to make something move. I'm now going to talk about nets and how we can tune their stiffness. So in 2050, I got a phone call from Professor Adi in the island of Réunion, who knew that I knew a little bit about membranes and nets, and he said, "Well, we have a problem. We have a problem in Réunion, and I don't know if you know where Réunion is. Réunion is actually a French island which is next to Madagascar. They mostly live from tourism, and actually they mostly live from surfing. And in Réunion, they have a couple of shark attacks, and of course, you only one shark attack and nobody wants to beach or your country or your island anymore. So this was really hurting the tourism industry. And so they had not found better than to, on their major beaches, install what they call shark nets. Right? So these are nets to keep the sharks out. And you see here a plan view. This is in Sao Paulo, so that's here the capital. And you see that line there, that's where they installed the net. This is what the original shark barrier net looked like. So they had chains here that were anchored to the seafloor, which is very difficult to do. Then you have chains here in buoys, and then you have polypropylene net, mesh. The mesh is such that the turtles can go through, but the sharks cannot go through. And then you have buoys. This is, although you can get all these materials from Home Depot, is extremely expensive net because it has to be installed by scuba divers, very expensive, and it has to be on a daily basis be checked to see if there are no holes in it. And after 2 to 3 months, it was broken. So I want you to look at the left-hand side to get an idea. Okay, broken. To get an idea about the net. I'm gonna try to, okay, I'll switch up the sound, but you get an idea, right, of where we are. So very expensive net, very expensive installation, very expensive maintenance, and broken after 2 or 3 months. I personally, well, the sharks that fly through it, but it was not the sharks, right? And so my intuition, people were in the workshop this morning, this has got to do, my intuition was like, well, I think they built it the wrong way. As in, they built the net, so you see there, the orthogonal net, right? It's like this. Now, this net is installed in the wave break. So that's basically where the water goes up and down, right? So the water is actually pulling on the buoys and then going down, pulling on the buoys and going down. And so you get kind of a cycling of a lot of tension, no tension, a lot of tension, no tension. And if you orient, which they have done in that design, if you orient your cables like this, it cannot become longer. Remember we talked about the bias, because that's what this is orthogonal, right? It cannot become longer. And so if it cannot become longer, there will be a lot of tension in your net. And you see that there with the simulations. You see there on the right-hand side, what if you do a hexagonal net? Actually, it can stretch a lot more. The other solution would be to orient it at 45 degrees, and it can also become a lot more. And so we did many studies. You see here, well, the number of elements. You see here the cumulative tension, and then you see different designs. And so we investigated these nets for wave coming like this, wave coming like that, wave coming like this. And as you can see, there's one very bad one, right? This one here. That has a lot of cumulative tension, which means cycling on, off, which can lead to fatigue, especially if you have in the net sand. You can actually break the net. And so, of course, this one here is the orthogonal one. Is that one? That's exactly the one they built, right? So they built from all the possible variations. They built the worst one. So yeah, this is too bad. Okay, so because I worked with nets, I was also a couple of years later contacted by two people. I was contacted by Rebecca Laser, she's a choreographer, and Janet Ekman, she's a visual artist who does these amazing net sculptures. And apparently one of Phoenix, somebody told me. But Janet's sculptures are hanging in the wind. So basically, they move very beautifully with the wind blowing. But Rebecca and Janet wanted to work together to see whether they could have their dancers interact with the net and whether the net could become like a dancer, right? And so as I started working with them, the dancers found that when they were loading the net in a specific way, it became very stiff. And if they were loading it in another way, it became very, also working with Janet, she was like, well, it has to be on the bias. So there was a lot of things that I already knew from the sharpness, which were kind of reinforcements. I'm going to show you a little bit. We did a workshop which took place actually over a couple of months at the University of Washington. And I'm going to show you an extract of this. Let me see what I can make it full screen. It takes about 1 minute, right? So this is after 3 or 4 months of a workshop in the architectural department where we worked with 14 master students in architecture, and Rebecca and Janet and Tyler Sprague working on how can we have the nets perform, not necessarily in an engineering way, right? But now how can we make the nets very dynamically responsive? So now we want to see when the dancers interact with the nets, we want to see a lot of movements, and then can we design the nets in such a way that they do that. So what you see here is at the end when with the students, when we had decided and prototyped and tested the nets, these are nets from the fishing industry, we had, I think, 4 days with professional dancers, and this is what you're going to see. So this is not a final performance, right? This is after 4 days of practicing. This project continues today, and will eventually be like a professional dance performance. Oh, and I'm going to try to put the sound back on. Okay. All right. Okay. I'm now going to turn, so I've talked about flexible shells and more semi-flexible shells. I've talked about flexible structures. I'm now going to turn towards rigid shells. And that's what we're doing this morning in the workshop. And I'm interested in seeing how rigid shells can take extreme loading. And actually, there's plenty of evidence if you type in shells and earthquakes or shells and tornadoes or any kind of like extreme loading, you will find pictures like this where you see an area completely devastated, but the shell is standing, right? And so we were interested in finding out why is that. And so we took this structure here, which is a structure by Felix Aldama in Mexico. It's a doubly curved shell, and it has withstood the 1985 earthquake. So we had the geometry for this, and we carried out analysis to find out why does this structure behave so well under an earthquake. So we carried out a linear dynamic statistical analysis to find the stresses, but more importantly, to find the eigenfrequencies. And basically, the earthquake in Mexico, peaked at 0.5 hertz, and the eigenfrequency, the eigenfrequency of the shell is 3.09 hertz. And basically, what happens in a structure, if you have if the eigenfrequency of the structure is very close to the frequency of the earthquake or of the waves or whatever you're looking at, you get these two frequencies very close, you get what we call resonance, and you can get a lot of damage. And so what we are finding is that for the shells, the eigenfrequencies are nowhere near the frequencies of the earthquake. And that is because this is the formula for eigenfrequency. It's the square root of the stiffness over the mass. So it has very high stiffness and very low mass. It has very low mass because it's very thin. And it is very stiff because it is very curved, right? So we're actually getting, because if we do the right form, we're getting stiffness for free. So that was very interesting for us to study. And so we started looking at, can we develop a technique to actually find shells or arches that are really good at resisting earthquakes. The first approach that we took is the graphic statics approach. Is basically where you draw the forces and then you find the truss line. So the one in the blue is just for gravity, and the one in the green is when you add in a horizontal force, which will represent the earthquake loading. And then you see here the resulting what we call truss line, right? So that is the line where the force is. And as long as that force is within the thickness of your structure doesn't collapse, right? So we found the truss line there for earthquake loading, which is the green one. And of course, the earthquake can come from both directions, so you have to mirror image it. So we there have like two truss lines now. If we define an envelope around this, this should be really the ideal shape for an arch under earthquake loading, okay? Now you might say, well, how are you going to build that? Because bricks don't really change thickness. But actually, if you think about the 3D printing capabilities that we have today, maybe this is possible. So we checked this with virtual work, and indeed this thing collapsed under 0.3 G, and that's the force that we designed it for. So that's for an arch, but we can also extrapolate this for how do we design a shell. So if we take those truss lines, and instead of taking the envelope, we kind of shift it half period onto the y-axis, and we do this a couple of times, and we love the surface to it, we end up with a very corrugated shell. So the idea is that this corrugated shell would be really good at taking earthquake loading. You might have never seen a shell like this. Actually, you might have, because in 1978, and Julian Lessig, on the left-hand side, designed these kind of corrugated shells as hangars. His shell is different from our shell because with him, the corrugation stays the same along the entire perimeter of the shell. With us, it's kind of slightly shifted. And so we did lots of studies on variations. And what did we vary? Well, we varied the depth of the corrugation as well as the periods. And that's there is this shell, right? That's our base model. That's what we're comparing everything with. And then we have like 5 variations. For example, you see here, this is a very long period and very deep. And then at the top, for example, FF3 and FF2, we have not so deep shell depth, but much shorter periods. And so we analyze all these shells using a pushover analysis. So pushover analysis is an analysis that pushes, and this thing that doesn't collapse at the first crack, but it collapses when you get in the case. And all of them collapse just like with the arch that I've shown you before, when there are a number of hinges forming. Now, what's interesting, everywhere where you see the blue, that's where a hinge, where you get cracking and eventually a hinge forms. And so you always get, in all of these models, you get always a hinge here and a hinge here. And then you get a hinge either here and here, or here and here. But you always get 4 hinges. That's exactly the way that an arch collapses. So what is kind of interesting to see is that when you have very deep corrugation depths, like for example in FF1 and in FF5, right, you get hinges developing here on the sides. And when you have very shallow corrugation depths, you get a hinge developing here, C at the top. And the reason for that is if you look at those geometries, so if we do a curvature analysis of this shape, we see that some areas are doubly curved, which is very stiff, and some areas are singly curved, but they are not so stiff. So if they are not so stiff, that means that under the loading, they're going to deform more. So they're going to crack first. And so, the geometries that I showed you before, some of them have, more singly curved areas at the top, and some have more singly curved areas on the sides. And that's going to determine where the hinges are forming. So now here's some values. So this is the DSA shell, right? So normally shells have to be designed for 0.3 G. So indeed, it fails at 0.3 G. These are all the same, same plan, same amount of materials, just the corrugation is different. And we see that, wow, this one here behaves much better, right? That one fails at 0.5 G. Same amount of material, also corrugated, but just the way that the corrugation is, it can just take much higher forces. So we're not adding mass, we're just doing something with the geometry so that it has increased capacity. And of course, the question is, how can we construct these shells? Because they were very popular in the 20th century, but people say you don't build that anymore because they're expensive to build. Because basically, if you want to build a shell, you first have to build forward, and you have to pass the concrete on forward. So basically, you first have to build a timber shell, pass the concrete on it, take the timber away, goes into the landfill, and so the formwork costs about 40% of the entire project. So we wanted to see, can we build shells without formwork? And I'm showing this project again. I'm sure you also, when we're talking about the things like this is the Santa Maria del Fiore in Firenze. It was completed in the 15th century, and the designer was an architect. Actually, it was not an architect, it was a co-creator, was Filippo Bertolini. And the rumor is that this dome was built without formwork. That's what is written down in the text, but nowhere do we have documents saying how they did that. We have all the documents about all the crane type machines that were the device to get the bricks up there, but no documents about how exactly did they do that, if they did that at all. And so we were interested in finding out whether you can actually do that. On the left-hand side, you see a drawing by Antonio da Zagnalo. So basically, those were the bases working with Brunelleschi. And you see on the left-hand side a plan view, and on the right-hand side, you see a cross-section. The plan view was remarkable is you see a spiral going, right? On the right-hand side, see, it's actually a double dome, right? So once you construct the inner dome, you can use that as scaffolding for the outer dome. So now we're interested in how can you build the inner dome without formwork. First though is, well, and actually the dome in Santa Maria del Fiore is not with spirals like this, but it has double spiral. But you might say, well, that's decorative element, right? It's actually goes up with a crystal. So they put sticker on it and put a beautiful painting on it. It's not decorative. Right? So what is this then? So we assumed two things. First of all, we assumed that the way that this dome was constructed was hoop per hoop. So they completed one layer And then another, a bit like the way you build it before, right? So not building it in ladders or anything, build, layer per layer per layer. And we also assume that the geometry is like this, that eventually it is kind of leaning inwards. And so we were interested in finding out how is this possible. So, as I said, two things. One is radial symmetry, meaning at some point, it's like, you're building a wall and at some point it starts leaning inwards. And the second one is you complete the horizontal forces. And so what we found is, so you have these horizontal forces, you have these things. These things, the dark gray ones, are what we call loxydromes. And they are kind of lodged every time in the layer below, right? So they're stuck. So here, this one is stuck in this layer and this layer. And I think it doesn't show on the next slide. We are going to look at this Playbonds, right? So if we look there, we see that we have these spiraling bricks which are stuck in the layer below. Once the wall or once the dome kind of starts leaning inwards, if you put the horizontal bricks, they would normally slide down, right? So we have there, this is from 3D. You see the bricks standing out, right? The herringbone bricks. You see the darker bricks would normally slide out if there is no friction between those angles. But from the moment that you have friction between your bricks, what happens is once the bricks start sliding inwards, they actually hit the herringbone bricks, and it's a bit like book stands. They kind of jam against that. And because of that, they cannot slide inwards and fall. And you see there on the top right-hand side, you see what happens if the friction angle between the bricks is 0. But this is, of course, not possible unless they're coated with Teflon. We found that from the moment that your friction angle is in the order of 10, and for mortar, this is really, yes, realistic values are 15 or 20. Because of the friction, these things kind of slide inwards and then collide with these bricks here and the bricks jamming. In that way, you can actually construct a structure where the bricks are just kind of sliding in, jamming. And what happens then when they start pushing against these herringbone bricks, but those herringbone bricks are stuck in the layer below, so they kind of transfer the forces to the layer below, etc. And that is how you can construct a dome. So we use Rhino to model this. This has more than 10,000 bricks, and we run a discrete angle analysis for each of them to make sure that the first of all will slide out, and secondly to make sure that the thrust line always remains in the dome, even when it's under construction. And that is basically how we think that the dome in Florence was built. So here we have Leslie, we have the dome, and that's of course interesting, but it's more interesting to see if in the 15th century we constructed a formwork. Can we use this technique today to also construct the formwork? And so we got the opportunity to work with SOM and the Create Lab at Princeton University, that's an architecture robotics lab, to see whether we can build a vault, a fortified vault, by positioning the bricks in a certain way and using the robots. So we're using 2 robots here. One robot we use to place a brick, and the other robot we use to support. The robots are very good at holding a brick for hours and hours in order, right? So can we do that and then construct an entire vault? And I'm going to show you a quick video of that. I hope that's going to work. Yep. I'll put the sound back on. Sound. So the way that this is constructed is first the arch was built, and then we built onto the arch. So the wonderful thing about robots is that they can position elements exactly in the XYZ location. Once they can keep it there forever. So first, the arch and built around that. So our role in that, we did not do the form finding of this fold. Our role in it here was to check the whether, by positioning the bricks in a certain way and the robot holding it in a specific way, whether this shell was stable at all phases of the construction and the arch. Okay, let me go to the next slide. Okay, I've come to my last project that I want to show you. Remember, I'm going to go back all the way to the beginning of my talk when I was talking about how I go to the shore in Sandy that caused so much damage, and how either people just rebuild one wall or they build these huge walls. Here's another example where they actually put lots of rocks, right? And so I was thinking there must be another way that we can actually build storm surge barriers that are only there when we need them. And I do not want to do it with mass, like just piling up a lot of concrete or piling up a lot of stones. I want to use this with form. So I want to use form to resist these very high loadings. So I want it to be deployable. I want form to resist it, and I want actually to use, water as a fluid. I want to use another fluid to resist it. And so my idea was to use, and I'm going to show you a rendering. This is not. I want to use big pressurized membranes that can be stored below the boardwalk, and when storm surge warning comes out, so in advance when this is going to come, they can be inflated. Of course, they will have complex mineralization, so if it breaks or it doesn't go down, it's probably a couple of layers. And this kind of technology has been used for much smaller dams, right? So these kind of things exist like at this scale here. What is new here is I wanted to investigate, can we use it at a much larger scale, and can we use this to resist the extreme loading of hurricane? Because when we get a storm surge, it's not just the water rising, that's one thing, but you also have the hydrodynamic loading of the water hitting, and then you have the waves, we're also breaking over there, so extreme enormous loads that come from this area. So, well, we didn't build a prototype of this because this is very big. So we actually looked at it for this area here, right? Remember that picture there? That's here. That's Rockaway Peninsula. And so I imagined like, oh, could we maybe build it along there, or along that boardwalk, so somewhere there. And as I mentioned before, so this is now a cross section, right? So if we have a membrane that we are going to inflate, there's two medium that you can inflate with, either with air or with water, or you can combine the two. But we look at why we air pressurize it. Can we pressure? Well, are the pressures that we need realistic? And are the stresses in the membrane realistic? Because they have to resist, on one hand, hydrostatic loading, they have to resist hydrodynamic loading and wave rate loading. And this is, of course, a complicated analysis because, first of all, these loads are complicated. And secondly, the structure itself is also very complicated. It's a non-linear structure, so it strains a lot, it moves a lot. And that is, of course, something that I'm thinking about, like the way that we typically design structures is that they shouldn't move, right? A footbridge, if you go on it, you don't want it to move, right? But with these barriers, it doesn't really matter if they deform or what, as long as they keep the water out and they don't break and they don't resonate, it's a safe structure. And so you see here, actually, we got loading. This is from Sandy, right? You see here, of course, you see the ebb and tide, but you see also how the loading gets higher and higher and higher. And so we analyzed, this is a very preliminary study, we analyzed how this big inflated structure would deform. So we checked deformation. Is the water always below the top of the balloon? Secondly, are the stresses so that the material doesn't break? And thirdly, what's the eigenfrequency of the balloon compared to the eigenfrequency of the waves? And see that the two don't coincide. And none of these things happened, right? So these were very preliminary studies. These were some other studies where we use finite element analysis. Actually, this is a cross section, right? And you see there's always four shapes that you can think of. If you just inflate it, it will be a semicircular arc, just like you inflate a balloon. Then if you have some water on this side, you will see it starts displacing. Then at some point, you get inversion of the membrane here. And this is a situation where you actually have water on both sides. And these four scenarios are actually scenarios that are recognized in literature. We done kind of sized it, and we found that, you know, for Rockaway Peninsula, for the loads that we had during Hurricane Sandy, such a balloon made out of a rubberized, made out of a vulcanized rubber with a nylon inside, it could actually take those loads, not deform too much, and not resonate. And that brings me really to the end of my presentation. So I hope that I'll be able to show that in structures, if we use geometry, there are extraordinary mechanics in there. They can do things that other structures cannot do. They can move a lot if you want that for your facades, or they can change their stiffness. That actually happens in the storm surge barrier in corrugated nets. Or they can take, if we corrugate in a certain way, they can take very high loading. And so, so I'm interested in the study of these very similar structures with the environment, particularly with extreme loads. I draw my inspiration, I'm showing you my inspiration from biology, but also from history. And I didn't show another project that looks at polylacing. So we use that. So I also use graphs to inspire, you know, how should we arrange patterns so that we get a specific behavior. And I'm also showing you how we develop numerical, graphical, and analytical methodologies to kind of study this kind of behavior. And all of this is really to find applications for the built environment, so at a large scale where gravity matters, where also time is a very important. I'd be happy to answer any questions. All the work, right? Okay. Yeah, I see some hands. Let's start here. Right. So the rain runs off, right? And now we just have gutters, and then the gutters take the water to the corners, and then at the corners actually we installed, I didn't tell you that, but the whole structure is not supported on the masonry walls. We actually cut in the corners and we installed huge steel columns in there, and so that's what we're doing. Yeah.
In your design proposal for the balloon barrier,
yeah,
how is that fastened to the stand? Is it just from the weight of water? Or is there...
No, you have to attach it to the. You have to attach it to something, right? Because otherwise the balloon will start going up. Yeah. And so you see here on the right-hand side, we did like the foundation study. So actually you need quite a lot. You know, we call it reinforced, reinforced concrete hydraulic ballast cases. So that will keep the balloon down. But then you also have the possibility that actually the water, especially with the sand, is going to go underneath. So you also need this skirt walls, and that is really to prevent the water from going underneath and coming up on the other side. But the idea would be, so it has, you know, quite a big concrete foundation. But the idea is when it's deflated, the balloon, you know, that's what the dotted line is, can be stowed underneath, and then you put the lid. I mean, I'm presenting it all very simple. It's not so simple, of course, but that's the idea. But you do need to tie it down. And we are actually also now taking this project further because so here it was really to stop the water out, but we're also, I want to go more extreme loading. So what about tsunami loading? There we cannot stop the water from coming out, but what we can do is actually redirect it to another place where there is maybe fumes, right? Not critical infrastructure. So that's the next study to see, like, if we have these inflatables, then we redirect the water flow towards where it's maybe more acceptable for the water to go. Yeah.
Thank you.
All right. Yep.
Yeah. It's more of a philosophical question. Some of those shapes that we have the result of mathematics. They come out of mathematical algorithms, optimization, or whatever it is. But mathematics, you have no idea how it's going to build or how much it's going to cost. So either is there any way to turn the mathematics Just like we think, as architecture engineers, that, oh, this is going to be too expensive, forget about it.
Yeah.
Is there any way?
Yeah, so these, well, first of all, these forms are very thin. So if you just calculate the material, we don't really use that much material. But if you build curved things, it's expensive because everything is planar. Wood is planar, glass is planar, steel is planar. And so, for example, what we did for the Dutch Marine Museum is a curved shape, and then we approximated it with straight, also it's actually segmented stone, like between point A and B, it's a straight line, it's not a curved line. And then also the glass, we adjusted the form slightly, so all the glass is flat because you can have curved glass, totally curved glass, but that mostly is made in China. So if one of the glass panels breaks, you have to order, first of all, it's very expensive using mold, and you have to make curved glass, and China is very expensive. So if we can, so what we did is we adjusted the form so that, it's maybe not totally hanging chain mold, but at least all the plastics are planar. It's kind of a trade-off. And then the other, so yeah, but so building curved things requires really a post-rationalization afterwards to see how can we do the same thing with the glass bricks. They are volumetric, straight, and they are not curved. So we have to do, so what we do there is how we kind of make the bricks. If you just stack them on top of each other, they become a straight wall. But there in the epoxy mortar, we can actually adjust it, keep the roller, hold it, so the epoxy kind of sits very fast in the epoxy, and then we move. So yeah, we have to engineer it so that
For post-processing, that computer people.
uh-huh.
You're doing post-processing.
Yeah,
Yeah.
yeah, but we do that with the computer, right? Like, for example, the data passes but we first find the shape of the shape, and then we're gonna just straight lines. Yeah.
How you are looking at this as a way to find it that comes from the asset system. I see this as any curvature here, that's energy that can be harnessed. And if we're trying to create models where things are reactive, are there people that are looking at a way to kind of harness that energy to then repurpose it into the same system and or harvest?
Yeah, so I don't really know that much, but it's I think it's a really good idea, right? If you get movement, then how can you get that energy? But so I don't, that's not my expertise. The two things. One, I know, for example, on bridges they try to do that. On bridges and move slightly, like get all the energy, but the payoff is not, like the amount of energy that you can get from that is not really worth the distance of the technology. But I will talk about the adaptive facades. I talk about how we put smart battery hours, but I think you have to run an electrical current to shorten it, right? So I'm now actually working with somebody in mechanical engineering and computer science to see can we actually use, and I know there's some people getting into materials, can we use materials because materials can do that. For example, if you look at bimetals are, it says it's two metals together. It's one material. I don't know what the word is, but they mix them together. But they have a different coefficient of thermal expansion. So under heat, it's warm, for example, here in Houston, the one metal will curve more, will want to extend more, and the other metal doesn't want to extend that much. So actually, it's going to start bending. So for example, that's one material that can actually respond to temperature. Another material is, for example, wood. Wood, if it gets wet, it will want to expand. So can we use that input externally, free external input to actually activate things? But that works well at a small scale, maybe of an adaptive facade, like this big, but it's very difficult to activate at a large scale. On the larger scale, I have seen this. Sometimes I can see, for example, pedestrian bridges. I think the opening close and do that by filling, a volume with water, right? And a lot of weight on this side up, and the bridge opens. Yeah, so I'm very interested in that, in using materials or using the counterweights that kind of slightly shift and then bring about a motion that I have not done before.
So, sorry, let me just I guess what I was really curious about is that you pointed out at the beginning of your lecture about how by 2050 it's going to be a 2.5 billion more people on the planet. And you wanted to talk about, and you mentioned how we can deal with 65% more floor space. Using, with your knowledge of shell form and geometry, how would you go about accommodating that in terms of like modularity?
Yeah, so that's actually a really good question because I'm showing storm surge barriers and large shells being concentrated on those. But actually there is research being done now at the University of Cambridge and also at ETH, where they're actually building floors, because mostly floors, not so much storm surge barriers or adaptive facades, really horizontal floors, and shells are curved, right? But so they are looking at systems at domestic scale. How can we make a floor that is a shell? And then on top of that, put a flat floor, and there's like little spots between the two. And you can, actually, my postdoc, my doing postdoc, to work on that and was saying how they make it out of prefab elements. So there's like 12 elements that we've done special shear locks, it locks together, and you can reconfigure it. And after it's use is gone, then you can actually take it apart. Because I think that's also very interesting. We are, we build buildings, and 10 years later, we deconstruct them and they go into the dump, right? But if we could, when we deconstruct, if we could recycle the elements and reassemble them into another architectural program that's more suited to our needs at that point, that would be very interesting. So I'm very interested in circular economy, right? That we can reuse the elements and then reassemble them into something else. But that comes with a lot of challenges because you have to make sure that your structural elements are still in very good shape. They have no defects and all that. So, and we are really far from that. But I'm thinking about it as I'm thinking about assembly and disassembly. Actually, one of my PhD students, Edward is doing, he's working on assembly, disassembly, and then reassembly into another shape. You have now a database of elements. Top 10,000 glass bricks. Now we need another kind of shape. What can you do with that?
Do you have prospective materials that would work in this balloon type of shape under the tremendous abrasion you might have?
Yeah, so so the materials for this balloon, right, they already exist. So that's a vulcanized rubber. It's about 1 to 2 inches thick. It has on the inside a nylon layer, which is very strong. So textiles can be extremely strong. But what we find when we unblend shells and membranes, the strength is not so much a problem, it's more deformation. Inside this membrane, they also have ceramic chips so that if there is debris, trees coming and rocks coming, right, that the ceramic chips will stop that. If they do not stop this, the membrane is not pressurized to its full strength. Because that's like a fully inflated balloon. If you pop that, the whole thing goes down, right? But if you have a balloon that's not fully inflated and you pop it, will go down very slowly. Or actually, with these membranes, what they have found is that actually it's not fully stressed before just solid state. And this kind of material that I'm talking about has already been used for underwater or dam technology. So it is kind of proven. The lifespan of it is also important. The lifespan of such a material is 25 years, not 200 years, not 50 years, but actually in the context of climate change, that might be a good thing, right? Because it's actually, and her colleague was working on it, it's not so, for structures that really have to deal with loading from climate change, it's not so advantageous to build a structure that is going to resist the loading that might occur in the next 100 years because our climate models are so, it can go like this, or it can go like this, go like this, or go like this, depending on what you do. And so it's not so efficient to design now, start and build a structure now for the worst case in 100 years. It's actually maybe more advantageous to every 20 years kind of adjust it, or another idea would be to actually build something that is good for the next 25 years and reevaluate the loading and then build higher, that's also research, but build higher and adjust, as you know, have more certainty about